Just in case somebody's really missed some classes, everybody's aware that there's no fourth test, yes? And everybody's aware what's happening Monday? Quiz, yes. Was it 15-7 through 16-1, which was decided upon democratically, loosely. Okay. So let me remember if we've talked about a couple of certain ideas. We did introduce the idea of conservative vector field, yes? I think we definitely did because I have it right on this page where we did something with it. One idea of a conservative vector field is that, well, can somebody tell me? Maybe you can use the picture to help you remember. What is one way to determine if a vector field is conservative? This is the not so practical way to do it. Oh wow, cool. Yes.
It's if you draw a closed loop, it will always be some always be zero.
Yes, all the contributions of the vector field around that closed loop will be zero. Okay, cool. Obviously, that's not a practical way to figure out if the vector field is conservative, because then you have to draw every possible closed loop and check every one of them. But it's really crazy useful the other way around. If somebody tells me, oh yeah, this vector field you got, it's conservative. And you're like, what? That means if I have any closed loop at all, then the integral around that loop in that vector field will come out to be zero, which really is the contributions from the vector field. I'll be going pushing against it and going with it kind of an equal amount of time, which is why it comes out to be zero. Let me stop for a minute. So this one was obviously not conservative. One major thing is the field itself is kind of rotational, yes? So immediately a circle drawn, if I try to integrate across, it's definitely not going to be zero. Because the thing is going to be helping me if I go this way. And of course, if I orient my curve to go this way, then it's going to be pushing against me and I get the negative of that. Somebody with me? So sometimes you could tell just by looking at it that it's not conservative. But you can't tell just by looking at it if it truly is conservative. Because then you have to check every little spot. It's like, holy no. Okay. So we're going to develop a way to determine if it's conservative. Now, something else I want to say. I think I said this last time, and I'm really sorry. Things have been insane as always. But I'm pretty sure that I pointed out that in a conservative field, vector field, there. If I choose any path to go along, and this would be like from A to B. This is A, Jeff. You're doing good, Jeff. A to B. So if I choose a path from A to B in a vector field, so I have this vector field, whatever it looks like, blah, 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 and I choose 2 points, A and B. I don't care how I connect them. If it's a conservative vector field, that line interval will come out the same. So we call that independent of path. So let me say this again. We saw an example where this was not true. We saw an example where if I went straight to it or if I went curved around to it, the line interval came out different. I don't know if you guys remember this. So we had an example where I had a field defined, and one approach from A to B was a straight line, and the other approach kind of bowed out like that. Okay, so we did that last time. And the reason the answer came out differently was, let me do this real quick. There we go. Oh my God. If I had, for example, if the vector field here was, let's say the vector field is just, let's say this. Yeah, the vector field is just x. So I'm integrating along the curve x ds. Then what I'm doing is I'm collecting all the values for x. So if I go along this route from A to B, I'm going to get some positive, some negative. If I go along this route, I'm going to get a whole lot of positive x values, yes? And some pretty big x values too. So by the time I get to the negative part, that's going to barely do anything to me. I need you to really understand what I just said. So if my integral is this, what that means is, as I travel along this path, I'm collecting those heights. So as I travel closer to the y-axis, my x gets smaller until it's 0, yes? And then back here it's negative. So that's going to come out barely positive. Do you guys see that? I've got more positive x's than negative. If I go along this route, I got a whole shitload of positive x's before I lose anything. So as I accumulate the values of this along these two paths, I'm going to get different answers for both paths. So this vector field cannot be conservative because it's path dependent. So if I have a conservative vector field, the answer to a line integral through it doesn't care how I go from A to B. Like it. So if I have a conservative vector field, leads to line integrals independent of path. So for example, we still have to figure out how to tell if something's conservative. We keep talking about how great it is. But if I have a conservative vector field, well, like this, if this was in a conservative vector field, if it wasn't this one, then it wouldn't matter how I traveled from A to B. I would accumulate the same amount. Either path, any path, even the ones I haven't drawn, every single path would come out to be the same answer. Let me stop for a minute. Now, that directly leads to the closed loop idea we had before. If I have a closed loop, so my A and my B are the same. So I start at A and I come back to A. So I'm going to call A and B are the same point. Are you guys with me? A little bit? No? Street jump? If it is, let me see if this is cool. So let me pick another point. Let me call it D, because we got C's running around already. So I'm going to call this way C1, and I'm going to call this C2. So C1 plus C2 makes the whole C. Does that make sense? So to get from A to B, I've got to travel C1, and then I got to travel C2. Yes? Let me see if you guys are cool with this. If I look at C2, if I go from D to B, all right, so let me write this. So if I try to go, integrate this, let me make this a vector field. And I can break this up into 2 bits here. C2 goes from D to B, correct? My assumption going into this example was that the field I'm operating under is conservative. Therefore, how else can I get from D to B? Do I have to go to C2? What's another way I can go to get from D to B? I can go negative C1, yeah? I need this to make sense. So the fact that a conservative vector field, if I try to do a line integral in a conservative vector field, it doesn't care how you get from your beginning to your end. Side note, that must mean somehow that all the contributions left and right, up and down, kind of like average, can add up to be the same thing no matter how you approach the other one. So we're going to look at actual conservative vector fields and see if we can see why it makes sense they're conservative. So let me see if everybody really understood what I just said. So to do this, because this is going from A to D, and then this is going from D to B, correct? If it's conservative, I don't have to go this way. I can go against C1, so that would be minus that. Doesn't that connect D to B? I'm sorry, D to B. So I go A to D, and then D to B. And does everybody agree with me that whatever this line integral is, this would be the negative of it? Is that cool? So of course, if I do that, I get 0. So if conservative vector field leads to line integrals that are independent of path, that leads to the idea that any closed loop in a conservative vector field has a line integral of 0. However much it gains here, it'll lose it going there, or vice versa. That's why we call it conservative. It conserves how much it's got. It doesn't get more, it doesn't get less if I do a whole closed loop. Okay. So something that would be really, really nice to know is, how the hell do you tell when a field is conservative, Jeff? Does anyone want to know? You guys want to know? Okay, good. Because I'm going to tell you. Even if you didn't want to know, it's going to tell you. So here's the cool little thing. Do you guys remember this dude? Yes. And if I have f of x, y, z, what was delta f? Does anyone remember? Fx of y, fz. This is a scalar function. What does that mean? That means for any input, I get a number answer, yes? If I have number inputs, I get a number answer. What is del f? What's the gradient of f? Sorry. What kind of thing is it? Is it scalar? It's a vector. Cool. I love it. Okay. So this is a vector. This is I could call this f. That's my vector field. So vector fields can exist on their own. They don't have to come from a gradient of another function. They can just be, we've seen vector fields, we've worked with them. They're just, somebody can just make one up and give it to me. Work with this. If the vector field comes from the gradient of a scalar function, oh shit. All scalar function means is a function that when you input numbers, it'll output a number. So is gradient f a scalar function? Why is gradient f not a scalar function? Because what is its output? Vector. So it's a vector function. You guys with me? So little f is a scalar function, correct? Maybe little f is x squared plus y squared minus 3z, yes? So for any number inputs, it will give me a scalar output, a number output. Okay, I love it. I like it. So if my vector field happens to be the gradient of a scalar function, then it's conservative. And it works the other way. If my vector field is conservative, then it must be the gradient of some scalar function. Okay. Every word I just said are words that we've seen before, we just haven't heard it put together the way I just did. So one part of this class involves the ability to do something like this. And let me see if you guys are cool. Let's go to 2 dimensions, yes? I like it. Okay. You would, Jeff. Can you guys take a moment and figure out the gradient of that? Oh, there it is. Yeah. Yeah. Okay. All right, let me catch up to you guys. So all you need to do is you need to make a two-component vector. The first component is just going to be the partial with respect to x. What's that?
6x
Yeah, minus 2y cubed. I like it. And then you have 3x squared,
minus
6xy squared. Kick ass. So if I set big ass f equal to gradient of little ass f, that vector field I'm describing would be conservative. Now, in this case, we created the gradient of f. I can see that it came from a scalar function. I can see it's a gradient. That's how we made it. So I know that field is conservative. Now, remind me. So this little piece is fx. This little piece is fy. If I did not know it came from a scalar function, what's one thing I could do to check? Do you guys remember what's got to be true about some of the second partials? Yeah. fxy equals fyx. The few functions that doesn't work for are obscure, piecewise defined monsters. So for almost everything we're going to look at, it's going to work. And that was the old French dude. Probably a young French dude, because nobody got old back in the day. Claire Rowe? I don't know if you guys remember that. Okay. So real quick, we know this should work, because we watched it happen. We watched it come from this dude. But what is fxy? 6x. All right, what's fyx? 6x minus 6y squared. Cool. So what do you do if you are given a vector field? And I'm going to show you more about why, if I know it's conservative, it kicks desperately so much ass. So I want to be able to check. If you give me a vector field, can I check it to see if it's conservative? Because if it is, a lot of what you have to do gets easier. So if I just give you a vector field, you should immediately just check the second partials, right? Not even the second partials. Let me say this. It'll just be in terms of the vector field. So if I gave you, if I gave you this, am I going to be able to think about it ahead of time? Maybe. Maybe. We'll see. All right. Let's see if I did this right. Even if I didn't, it's fine. So I give you that vector field, yes? And you're going to have to do this line interval. It's going to be kind of gross. Oh, shit. How do you check if this is conservative? If this is conservative, where must 3x squared y squared minus 1, where must it have come from? A little fx, yes. It must have been the partial of some f, yes? So that already, if it is based on the gradient, that would be fx. And what would 2x cubed y? That would be fy. So how do I check to see if that's true? I take this, we'll call it p, and I'll do dp dy. And what's that? Yeah, 6x squared y. And what would I check that against? I'll call this q. dq dx, and what would you get? Holy shit! Sorry. I'm just very happy that actually worked the way I wanted. Even if it didn't, it would have still been like, oh, it's not conservative. So we don't know yet the full scope of why it's good to know it's conservative. So we'll do that next. But you guys see how simple it is now to check to see if a given vector field is conservative. What this means is, if you plot out that vector field, any closed loop you look at will have a line interval of 0. You can actually see it physically. You can see all the contributions kind of like negating each other as you go around the whole thing. Are you guys with me? That's part of what we did last time. Okay. So what is the usefulness of knowing that this is conservative, Jeff? Well, what if I want to, in fact, let me take a step back. Do you guys remember F-Talk? Well, I call it F-Talk. I don't know what your teacher called it, but the Fundamental Theorem of Calculus Part 2. It's the damn thing that got everything started. This is where the big ass F's came from, right? Not in terms of grades, but in terms of the writing of this. Not very good. F-Talk 2 said the integral of little f is equal to the antiderivative of f, which we would write as big ass F, evaluated at the endpoint subtraction, right? It's the underpinning of how we do integration. So it just says this. It says, if I integrate a function from a to b, that is equal to the antiderivative evaluated at each endpoint, the difference of those. Okay, so this ruled a lot of our lives, and it just never quite goes away, which is good because it's really easy. What that means is there's a lot there. This is going to come into play later today again. If I wanted the area, do you see how the answer just tells me I just care about the values at the ends? Plug in some function. So to get the area of this thing, I just look at the beginning and plug it in, and look at the end and plug it in. That is what that damn thing says. Yes? Which should still trip you up. Which should still be like, holy shit, that's weird. Now, hopefully, whoever you had as a teacher kind of showed you where this comes from. It's a really cool idea. But it's still trippy when you think about it. To get this area, I just have to plug this and this into a certain function. And then it gives me the area. So sort of ignore the area, and then I get the area. Do you guys understand what I'm saying? So that's going to come into play really big later today. So that's great, Jeff. That's Math 180. Stop reminding me about how easy I had it before. So now what happens, and one thing I want to point out. So what is little f compared to big ass F? What's the comparison there? How do they relate to each other? Big ass F is the antiderivative of F. So what is little ass F? It is the so I could rewrite this as, yes? You guys with me? Now that you've gone through Calc 1, you can go back and say, well, that's what the hell it is, and then look at this shit. Bam, integral d whatever is whatever, evaluated from a to b, okay. Yes? So when I integrate a derivative, I undo the derivative. That is essentially what it's saying, which is more like what F-Talk 1 directly talked about, but that's what this kind of hides. All right, how are we doing? Does that sound at all familiar? No? Some of you guys are like, just keep going. So, what happens now, if I'm given this problem, and I know f is conservative, yes? If I know f is conservative, can somebody remind me how can I rewrite big ass F? What must it come from? The gradient of little f. That is like what I did here, yes? I rewrote big ass, little, in this case it's the other way around, but I think you get the idea. I rewrote this as the derivative, which is a one-dimensional form of the gradient of another function, right? So I have the integral of a derivative of a little function. Somebody with me? If the vector field is conservative, I know it can be expressed as the gradient of some little function. Yes? So what do you think is going to happen? What's the fundamental thing that's about to happen? Because you know how integrals, how they act with derivatives. So what I really should end up getting is just little f. Evaluated at the endpoints. Yes? So this would be and I should have defined, yeah, Jeff, you put it on the next line. Good job. Let's say that C is from A to B. Yes? So I got my R of T goes from T of A and T to B, T equals B. What this becomes then is just F of R of B minus F of R of A. So in this case, do I need to, do I actually need to figure out the C? Do I need to figure out the path? Do I need to figure out the parameterization? Do I need to do all? No, I can just go straight to the end. This is kind of related to, when I integrate to find an area, I don't worry about the area, I just worry about the beginning and the end. Same idea here. If I want to do a line integral through this thing, if it's conservative, it shouldn't matter what path, which means I don't have to parameterize the path, because it doesn't matter. I just care about the beginning and the end. This is exactly like F top 2. Maybe, Jeff. So let's do this. Now that I've got you maybe understanding why it's so good to know if F is conservative, because this just kicks a lot of ass, let's look back at this handout from last time. We haven't done this yet, but I want to immediately do number 4. Look at number 4. Can you first start off? Yeah, that's why that was in my head, because it's almost like this. Can you first verify that's a conservative vector field? Let me know if you discover it isn't. Because if it isn't, that really sucks. I want it to be. Oh, there. Where can I put you? Nowhere safe. Okay. If you want it, here it is. Come and get it. Now, things get interesting on part B, but let's see. Let me catch up to you. So, let's say this is P and this is Q. How do I check to see if this is conservative? D rho D Y, because it's already fx, isn't it? If, and I don't know yet, but if this did come from little f, that first entry is fx, and the second entry is fy. How do I check if it did? Well, the second partial should meet. So if I take the derivative of the one that was already with respect to x, that's the first thing. If I take the derivative of that with respect to y, that's the equivalent of fxy. And then the second one would be I want to do dq dx. So what is dp dy?
3x squared y squared.
Okay. And what is dq dx? Thank the gods. Okay. Good job, past Jeff. Yay. Okay. Yes?
Can you not call it fx and fy because you don't actually know if it is?
Exactly. I don't know if it is. I want you to understand why I'm doing what I'm doing, because if it is f, that's already fx, so of course I'm going to do with respect to y now to compare it to the other one. So I want you to understand why I'm doing that, but I can't call it fx because I don't know. I don't know yet, right? All I have to do is put a fourth power here. And then what I wrote, if I write that, it was a lie. Does that make sense? Yeah. Okay, now I know that that is fx and that is fy. Okay, I like it. Kick ass. Okay, now, here's where things get trippy. We have just proven, what this means is that f exists. So that delta f gives me my big ass vector field, yes? So now the question is, so the line integrals that I have to do, if I know what little f is, they become much easier. Because then I can just use that little straight to the answer, f of r of b and f minus f of r of a, yes? How do I figure out what little f was? So now I come in and do like you just said. What have I verified fx is? No. You don't have to do shit. What is fx? X squared y cubed. I love it. And what is fy? Kick ass. Now, if I integrate, and it is going to be a partial integral, but don't make too big of a deal out of it, really. If that is fx, how did somebody get to it? How did somebody start with f and get here? They treated y like a constant. So when I undo this differential, I'm considering y to be a constant, because that's the only way I can undo it. Does that make sense? There's nothing excessive about what I'm doing. I'm just treating y like a constant to go backwards, the way they treated y like a constant to go forwards, to get here, yes? So what do you get if you integrate this, treating y like a constant?
1/3 x cubed y to the third plus c.
And now here's the trick. Okay, you ready? I love that, Zach. Don't put the c yet, though. Don't put c. If I'm doing a normal integral, the constant would be a true constant, because the derivative of a constant is 0. What does this process we just did consider to be a constant? Even more than that. What about y squared? Is that a constant? What about the sine of y? What about the natural log of the cotangent of y over the square root of 1 minus the natural log of y? That shit is a constant. Yes? So, I want this to make nothing but sense. In 180, we integrate. We're only taking into consideration one variable at a time. So when I integrate, I get plus c, because it had to be a number for the derivative to be 0. But this treats every function of y as if it's a constant. So thank the gods, we don't have to write every function of y here. We just write every function of y here. Like that. Now to me, that is a very slightly cool idea. This was really cool to me when I first learned this. Does that make sense? That's a consequence of how we do partial differentiation. Now, what the shit? How do I figure out what the hell g is? I have information, right? So, are we not saying, do you all agree this must be what f is? This has everything that f could be. It's got the thing that leads to this, and it's got everything else that would have died. Yes? So somehow I've got to figure out what g is.
Does g of y also cover like the plus, if there was like a
Yes.
2?
G of y could be y squared plus 2.
Okay.
So g of y has the plus c in it. Because if I said y squared plus 7y plus 3, you'd say that's a function of y. Even though there's a plus 3, that's a part of the function of y. Good question, though. That does have that in there. So you don't have to put a plus c on in addition. That would suck. That's really much. Anyone have a suggestion? What's the other information that I know for sure? I know fy. And we just said f has got to look like this. So if I start here, what is fy? If I start here, what is fy? Do it. Do this. Yes? Yes? X cubed squared plus? No. What am I taking? Derivative. And this is a function of y, so this would be g prime. If g of y was sine y, and you took the derivative of this, wouldn't you put this plus cosine y? So whatever gy is, what am I going to put here is derivative. Now we understand in this case that prime is with respect to y. And I don't have to put dg dy if I don't want to, because it's understood because of this. So we know that prime means derivative with respect to y. Okay. Love you guys. How we doing? You guys okay? If if you understand that G of Y has to be there, the next level is neat. The only other information I have is Fy, and I currently have a form for F. The only way I can make those work together is if I calculate Fy on what I know. So what must G prime of Y be then? 2. So then what's G of Y? Now, some of you guys might realize plus C, but we don't need that. And that's because what I'm going to use this for is to evaluate this integral. So there's going to be like integral r, f of r of b minus f of r of a, so whatever the c would have been, it would cancel. But the y is going to contribute to this integral. So if I were, so what is f? 1/3 x cubed y cubed plus 2y. Kick ass. And somebody help me out. We're going from, yeah, it tells me right here. Sorry, I forgot. So this tells me what my t's are, yes? So if I want to do this integral, I can go straight to the answer. This is going to be f of r of b minus f of r of a. So this will be f of r of negative, r of 0 minus f of r of negative 1. Now this is always, like anything in this class, it has an analogous part in Math 180. It's just got more stuff to it. We're in another dimension, we got freaking parameterizations going on, blah, blah, blah. If you compare that work we just did so far for part C to what we did for other line integrals, that a lot easier. Because now my whole job is plug shit in. My whole job is just plug stuff in. What is r of 0? Well, be more specific. 0, 0, yes? Because what does f need for inputs? Points, yes? What is r of negative 1? Yeah, it'd be negative 1 plus 2, so it's 1. It'd be negative 1 minus 2, negative 3. So what's f of 0, 0? 0. Is there, let me stop for a minute. This is the other thing that has another layer to it. Our damn functions have points for inputs. So r of 0 is a point. It's what point does that vector point to when t is 0? It points at 0, 0. What point does that vector point to when t is negative 1? 1, negative 3. Those are now my inputs for my poor little f dude. Yes, it's a multivariable function. It needs more stuff. So f of 0, 0 is 0. What's f of 1, negative 3? I don't know. So do it again. Sure, man. Let's see. I haven't done it yet. Let's see. It'll be negative 9, yes? Minus 6, yeah, good. So minus negative 15, so we get 15. Now I want you to look back at any line interval we've done before. None of what we've done would have fit in that little bit of room. Right? Okay, maybe, all right, let's do this. So I've got conservative vector fields down for you. I've explained why they're really valuable. I've shown you how to tell if what you're working with is a conservative vector field, and if it is, you go, thank the gods. So let's take a step back from here, just to remember how it works the other way. Can you guys, number 2, we haven't really done yet. I don't know if anybody's tried these out yet. But a big part of this whole thing before you get to conservative vector fields and all that, you're lucky if it's conservative. Just think about it like that. I'm going to generally need to be able to figure out the parameterization of the specific path I'm taking. And if it's conservative, it doesn't matter. I don't need to take a specific path. That's why I end up with an easier process for it. So, 2a. So I want you to parameterize the line segment from 1, -1 to 2, 3. How do you guys feel about that? Could you do that? We've done ones like this before. In fact, I think the very first one we did was like this. Yeah, there we go. Yeah, just reminding us, we did this little dude here. C was the line segment from there to there. We got parametric equations. I think this one specifically, somebody had a different set of parametric equations. So how many ways are there to parameterize a path? Infinite. How many of those are generally useful? Not infinite. Okay. So how do I do this? I want x as a function of t, and I want y as a function of t. One way somebody did this was to actually stop and do the algebra and figure out the equation of the line, and then use let x equal t and then y is whatever it is from the equation of the line. Let's do this a different way. So what if I said x is t? Well, this will end up in the same place, but we'll see if you guys are cool with this. What would y have to be? So when x is 1, y is -1. And when x is 2, y is 3. I wonder if I did the other way for you guys already. I don't think so. No. One way to do this, let me show you. All right, here. Let me do this other way, and then I'll let you guys pick. If I say this is t equals 0 and t equals 1. So make sure that you can't which point has to be first? 1, -1, because I'm starting there and going to 2, 3. So if that is t is 0, and that is t is 1, what's x? When t is 0, x is 1. When t is 1, x is 2. T plus 1, yeah. And then what's y? When t is 0, y is -1. When t is 1, y is 3. Yeah, so you know it's going to be like something -1, right? And then to make this work, it'd have to be 4t. So when t is 0, you get -1. And when t is 1, you get 3. That's the way I always do it. If you instead want to do where you first figure out the algebraic equation of the line, you can do it that way. But I want you to realize that we are going to be having some parameterization to do with points in three-dimensional space. So finding the equation of that line will be a little bit harder. It'll be like a whole problem in its own. How do you guys feel? So there are several acceptable answers to any individual parameterization question. You can either always do this, and this is what I always did when I was a student. I just made the first point 0 and the second point 1. That made my limits 0 to 1, which always kicked a lot of ass. Yes? If you solve first for y equals mx plus b and then let x equals t, then the limit in your interval could be anything, which could increase the amount of work at the end. I don't know if you guys are with me at all. So there are options for you. Did somebody else get a different parameterization? Did anyone do it a different way?
I touched on the equation of the line.
Yeah.
X equals t and y equals 14 minus 5.
So y equals
4t minus 5.
14. 4. Oh, 4. So you found y equals 4x minus 5. So then you said x is t, and y is 4t minus 5.
Yeah.
And what would your t go from to?
I'll go from 1 to 2.
From 1 to 2, yeah, because your x is t. Yeah, I like it. Cool. So it's a bit of a trade-off. Whatever makes more sense. And if they both make sense, I would choose the way that lets one of your inputs be 0. Because normally that's like the preferred input for your limit on your integral. So try to do part B. This is a circle, so we've talked about this. And of course, part C is an example of what I just said a minute ago. Okay. So what do you guys think about this? It's a circle, which should kind of give you a little bit of a hint as to what you want to do here. I don't want to use the equation of a circle, dear God, because then you have to square root, plus or minus, if you pick the right one, blah, blah, blah. What's a better way to parameterize a circle? Yeah, so, and to be honest, it really doesn't matter which one you call which. It's just going to affect what your t goes from to. But in general, we're used to calling x cosine, y sine. What's the radius of the circle? Good, because it's just a quarter circle, so the radius is 2. And if you want to call this cosine t and you call this sine t, it really doesn't matter. But then, what does t go from to? Yeah, so if you start at 0, so it's supposed to start at 2, 0, correct? So good, if you start at 0, then cosine is 1, sine is 0, so then you get 2, 0. And then you're supposed to end at 0, 2, which of course is on the y-axis, so then you just want to be at pi over 2. Is that okay? Okay. And, as always, if I would have thought about it, this one's not that hard, but it's not a bad idea to sketch out what it is you're working with. So if you can see it, you might be able to tell what to do with it better. And the angles would be easier to think about if you sketch that out. Yes?
I don't understand. Y equals 2 cosine t, and y equals 2 sine t.
What is the equation of a circle?
X squared plus y squared equals r squared.
So in this case, it's x squared plus y squared equals 4, right?
Yeah.
If you let... let's see. In general, anytime you have a circle, especially when if it's not centered at the origin, you have to adjust it. But if it's centered at the origin, it's definitely beautiful. So if I do let x be 2 cosine theta, or t, sorry, and I let y be 2 sine t, what do I get? 4 cosine squared plus 4 sine squared. And what does that equal?
4.
So therefore, this is that equation. So this parameterization, x is 2 cosine t and y is 2 sine t, works. If you have a circle centered at the origin, I'm going to choose that parameterization. And the great thing is, what made this happen in the correct, obviously it had to be here, from 2, 0 to 0, 2. What if I wanted to go from, in that case it's very blatant, but if I wanted to go from negative 2, 0 I'm sorry, negative 0, 2 to 2, 0, yes? What would have changed? Yes, good, the limits on the t. That's all I would have had to change. So x equals 2 cosine t, y equals 2 sine t, by itself, for every value of t, makes the circle of radius 4, yes? I'm sorry, yes, radius 2. And if I just want a piece of it, I just have to make t the appropriate angles to just pick out that piece of it. So just like we saw when we dealt with polar coordinates, cylindrical coordinates, when I see circular stuff, I think x squared plus y squared. I think r cosine theta. That's really all that is. R is 2, theta is t, x is r cosine theta, y is r sine theta. So you can even think of it like that. It's sort of a hidden little polar switch. How do I do part C?
You can do t equals 0 to t equals 1 stuff like. Because it's a 1 second.
Yeah, because you can treat x, y, and z as each of them their own problem. Yes, so I can do it just like I did the first one, right? Does anyone know a different way to do that one? Now, I was shit talking about finding the equation of the line, but to be honest, if I find the equation of the line, it involves parameterization. I don't know if you guys remember. Can somebody tell me the direction vector for this line? How do you figure out the direction vector for the line? I know. Right now you're all like, holy shit, the directional derivative? Do I have to do a gradient? Do I have to? No. It started at 2, negative 3, 5. It then went to negative 1, 4, 3. What is the vector that represents the direction it went in? Yeah. Wait, do it again. Good, because it was a 2, went to negative 1. So the direction vector is what that word says. Is negative 1 minus 2 is negative 3. So I had to go down 3 from 2. Had to go up how much from here? 7. And then I had to go down 2. Kick ass. So that would be 2, negative 3, 5 plus t times negative 3, 7, negative 2. So if t is 0, I get this, yes? Yeah. If t is 1, I get that. And to be really honest, everything we just did, you can actually do it in 2 dimensions too. So hopefully that feels a little familiar, because that's part of what we had to do towards the beginning of the class, was just find the equation of the line through 2 points. What do you need to find? The slope? That's what this represents in 3 dimensions. That's the slope. Slope can't be a ratio anymore because it's got 3 directions it can move, not just 2. And a point. And now we realize, so what did I just say? What's the t got to go from to? 0 to 1, yes. Cool. Sorry, that's for this problem. Did we do number? We probably didn't do number 3, did we? Okay, let's look at 3. So just to remind you of the work it would take if I didn't have a conservative vector field. What's the first thing you should work on for number 3?
C.
Yeah, what's the parameterization of that that route? Ooh.
Just T1, 2, 3.
Yeah, this one's nice because it started at the origin. Yes? So what is my parameterization? What's my R of t? Or let me see it more clearly. What's x, y, z?
X equals t equals
T, 2t, 3t. Cool. What part of that beginning integral is kind of so difficult to work with directly that you almost never see us work with it directly? What's part of that interval? Well, it's not x e to the y z. It can't be c because we have. What's the only thing left? ds. ds is the change in arc length, which is really difficult to work with directly because my freaking curve is moving, and if it's going faster here, then the arc length is bigger. If it's going slower here, the arc length is slower. So ds actually changes as I move through. So it is not easy to work with directly. So what do I want to replace it with? Oh my gosh. No, dear God, no. Yeah, all that business. So just to kind of shortcut it, we talked about this last time. I can rewrite this as this evaluated at these points. Let me zoom out. This is getting a little busy here. Here, let me see. Do I have another copy? Here we go. Let me just focus on this one problem. It's a little bit crazy. So I've got my r of t is t, 2t, 3t. Yes? And then this integral can be written as, I can put the values in here, right? What's x? T. What's y? 2t. And what's z? So what's yz? 6t squared. And this I could replace with, what am I trying to say? R prime. What's R prime? 1, 2, 3. And I just need the length of it. Because if I want to make this dt, then that would be r, the length of r prime, divided by, let me see if I can remember. It's been a while. It's been a minute. Well, here, what's the length of r prime? Yeah, 1 plus 4 plus 9. So that'll be square root of 14. So this will be square root of 14 dt, because ds is the length of r prime dt. So we talked about that last time. That's the connection between ds, which is very difficult, and dt, which is very straightforward. The trade-off is you get this extra little component. Why was it so nice here? Because every component is at most a first degree in t. So that's a huge trade-off, though, because for just some random r, I could get these funky functions of t, and then this piece will become a problem. Yes? Is that a very difficult integral to do? No. U sub, exactly. Let me stop. So. Oh yeah. From right here, what's t going from to? Yeah, 0 to 1. 0 to 1. So if you follow that process of, you see how we just did the same thing we did for this last problem? It just was easier because the first point was 0, 0, 0. So it's the direction vector times t plus the initial, which just ended up being that. If you do that, t will always go from 0 to 1. Which ends up with a lot of your integrals being easier to work with. Okay, I almost don't care about this because now it's easy. Now this is math 180, yes? Okay. Yeah. Oh, sure. Okay, we already did that. Yeah, we already did that. Good. Sorry, I'm catching up with where I am. Oh, just to point out a couple things. You're going to see some of these words showing up. Smooth, we already talked about. It makes sense that it's got to be continuous. But the reason we don't let it be 0 is because if it becomes 0, it can suddenly turn and go a different way, and you get these kinks in your graph. So we don't want r prime to be 0. By the way, this is on this page here. If you don't have this, you desperately want it. Yes? These two are going to come up here in a minute, open and closed. What else did we talk about? I think this might have come up, but it's going to come up here in a minute. So there's definitions right in the middle of this page of notes. Independent of path we talked about, so that's here. So right here, if D is an open connected region. So what does that mean? That means open means it does not contain its boundary points. Which means it could be something like this. So it just doesn't contain its boundary points. Connected means any 2 points in the region can be joined by a path that lies in D. So there's nothing that's kind of like, there's no region that has separate parts of it. I have to be able to get from one part. So this region would not be simply connected, and this region is not simply connected. I can't go from this piece to that piece. I can't connect them and stay inside the region. So it's kind of like the 3D analog of no jumps, it's got to be continuous, these kind of things. Okay. A simple curve is a curve that does not intersect itself. So this is a non-simple curve. I feel like I talked about that before, but maybe not. This is also a little fish. So a simple curve just does not intersect itself. So this is bad. Sorry, fish, you're bad. And then simply connected is what I just said here. Well, actually, this is different. This connected. Simply connected is basically there's no holes in there. There's no holes inside my region. Okay. Those are very, those almost will never come into play for the problems we're going to look at. If you go much further in mathematics, then you have to be really careful about each of these things. For almost every function we look at, these are going to be true. So like in Math 180, you had to have a continuous function. You almost always did. Had to be differentiable. It almost always is. Okay. Blah, 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 blah. Oh, then we're getting down to here. This is why I call them P and Q, because that's going to become big in a future section. But this is basically just saying what we did. If I have a vector field and I take the other partials of each piece, if they're equal, that's Clairaut's theorem. That means it must have come from a little f. Okay. These last two sound very familiar, are very similar, because this is if the conservative, then this is true. This is if this is true, then conservative. So it goes both ways. Do it again?
The thing that's in front of all the grades.
Yeah, it's the computer's font way of trying to say delta. Yeah. So it's exceptionally freaky. All right, so what we're about to get into is called Green's theorem. Do you guys want a break? Yeah? 5 minutes. We'll come back at 1:45. We'll take a little break. Let your brains go air out for a bit. All right, guys, just to get us moving in the direction of the next section. Let's say I'm given a vector function, vector field, pi hat plus qj hat. P and q are both functions of x and y.
This is 16.
Sort of. It's getting in that direction. It's kind of like a bridge. Then, if I want to do this, if I want to throw a poor little line integral path into this vector field and figure out what it experiences as it goes through it, yes? Because one way you can think about it is I'm pushing against the wind, or I'm going into an electric field. This is just trying to figure out what's happening to the poor little dude going along this path in this field. That's what that does. I can then just replace f with what they told me it was, right? That's amazing. The step I just took, ground shaking. No, I just plugged the shit in. What is this? That is a vector. Do you see that? This vector is this is going to be d by dx. I just lost my train of thought. These things happen, Jeff. No. This is going to be dx dy, this vector. So dr is the vector that contains the infinitesimals in all the different directions. So if I was in 3 dimensions, it would be dx dy dz. So I've got 2 different notations here for my vectors, and I apologize for that, but if I write them in both the same notation, let me do this. Normally we put the I hat in front and the j hat in front, just so it doesn't look like I'm taking the derivative of a unit vector. So all I did was they give me a vector field. A vector field has to be in the form of a vector, so it's got an I component and a j component, correct? I put that in. I rewrite this in terms of its vector form. How does a dot product work? What's I dot I? Well, no, come on, no.
0.
How does a dot product work? It'll be 0 if the 2 things I'm dotting are perpendicular or orthogonal. Right? Linear people are like, there's so many points. You with me? Is I orthogonal to I? No, of course not. It lies along the same direction. How long is I? How long is I? What is I's job? I's job is to just contain direction information for the x-axis. Therefore, it cannot have a length. It has a length of 1. It cannot affect somebody else's length. Yes? For my 284 people, it's part of the basic set of vectors. So pi dot I dx is just p dx. I dot I is 1. It's officially the length of I squared, but that's still just 1. Yes? What is I dot j? Which way is j pointing? The y direction. And I is pointing x direction. So what's I dot j? 0. So this dotted with this is p dx. This dotted with this is 0. This dotted with this is 0. This dotted with this is q dy. Now, that is a trippy ass way to be presented an interval with, right? So that interval in front goes with both dx and dy. Yes?
What happens to that I and j in the previous video?
I dot I is 1. J dot j is 1. If you dot a vector with itself, you get the length of the vector squared. They have length 1.
Well, what about when you dot I with j?
I dot j is 0 because they're perpendicular. Yeah. What about I dot I, Jeff? So here's an idea. Here's this thing. Here's what's going on. This is like an integral in Math 180. It's one integral. Yes? No, it's not an integral in Math 180 because it's got a dx and a dy. But it's a single integral, correct? Okay. Yes. In Math 180, what are we normally letting change as we examine a function? We're normally just letting x change, correct? So therefore, dy in Math 180 would have been 0. So therefore, it would have become a normal Math 180 integral. C would lie along the x-axis because that's the only way it can go in. Are you guys at all with me? So this is just another way to look at us allowing for a different way to go. Do you remember one of the first things I did with you guys when we got into double integration was I did a problem for 180 with a double integral instead of a single? Okay. I think you all would agree with me that the double integrals made it a little bit harder. It is kind of unnecessary at that point because we were assuming the height to be 1, so I didn't need it, correct? This is going to be an example where if I can rewrite this problem in the terms of a double integral, the work becomes a lot easier, believe it or not. So, here's kind of the idea. I want to investigate a double integral of something by itself. Let's look at this. Yeah. Yes, because q is a function of x and y. So, watch this. What's dA in the way I have things formulated right now? What should dA be? Either dx dy or dy dx, yes? Do you guys see why I might want it to be dx dy? So I can write this as, oops. Yeah, I want to keep things a little vague for right now. These two fundamentally cancel. Because the inner integral is all about keeping y constants, all the x stuff are kind of related to each other, so those two cancel. So if I just focus on this inner integral right here, so I have integral dy on the outside, and what do I have left on the inside? Integral dq, yes? Good! Sorry. This integral of q dy. I'm attempting to bypass about 30 minutes worth of full explanation. Nobody got time for that right now. But this is actually pretty close to what's important about this. Does everybody kind of follow that chain of thought? No? Isn't that a piece of integral dq dy? Yes? Okay. Now here's what's trippy. Because we're going to be, eventually we're going to be going around these closed loops. Some of the time I'm going to be going forward with respect to y, some of the time I'm going to be going backwards with respect to, x, backwards, and then sometimes I'm going to be going forward with respect to y and going backwards with respect to y. And we normally choose a counterclockwise direction. Everything we do is kind of built on that assumption. Because of the fact I've chosen that direction to go, here's what happens. We've already seen one little piece. So when I write this out, there's only going to be one thing that's going to be very kind of out of place. So if I start with this, this becomes this business here. First thing, it's going to look very familiar. Yay! dA, yes? That piece, and there's room here, of course, because I got to deal with this guy, right? So this piece is related to this, that with the dx, yes. Okay. Because I'm going back around myself at some points, that is what ends up leading to this fact. If I would have chosen a clockwise rotation, the p term would have been positive and the q term would have been negative. Let me see, I feel like I forgot one thing. No, you didn't. Good job, Jeff. Oh, this book is silly. Where do they put it? That's okay, Jeff. Eventually they do this. Yes, this should be, now here, let me add one little thing on here. Because the book sort of wavers around, it doesn't do this all the time. If I put this little symbol on my integral, that means it's a closed curve. So if you don't see a little circle on your integral, that means it's just a path that doesn't have to close. If you see a little circle on your integral, that's got to be a closed path. It's going to come back on itself. Now, real quick, can you guys remind me? If I give you a conservative vector field, everybody write this after me. If I give you F equals Pi plus Qj, yes? How do you check? I didn't say it's, well, how do you check to see if it's conservative?
P equals Q.
No.
Fxy equals y.
Yes. So Pi plus Qj. You would take the partial of P with respect to y. Good, because that's the first part. It must have come from fx, so it did. You would take partial of P with respect to y, and you check to see if it's the same as partial Q with respect to x, yes? If they are the same, it's a conservative field, yes? If they're the same, what's this shit? Closed curve, conservative field leads to a zero integral. Yes? So thank God, if we do new math, it better do the same shit we just did, or else we're going to throw it all away and go somewhere else. So this is new, but it better give me the same result that we got earlier. Yes? If this is conservative, these are equal. That's zero, which matches with the idea that a closed curve should have a zero line integral for a conservative vector field. Oh my God. Okay, maybe. Man, for a moment I thought I had you guys. And now you're all back to, oh my God. Okay. What this is called is Green's theorem. Oh, that's why it sounded familiar. A problem we did earlier. Let me see. I don't want to do all that. No. Here we go. Let's try one example. Oh, good. I got time. Look at me go. I'm amazed. Okay. I want to integrate this. Let's try a concrete example, which is what everybody always is clamoring for, and I don't blame you a damn bit. So look at that. Now, obviously, if it's a conservative vector field, I don't have to do a damn bit of work. This is just as easy as the other formulation would be if it's conservative. Zero, I'm done, correct? Can you guys just look at that and tell it's not conservative?
Mm-hmm.
Hell yeah, what's that, squares and cubes, you know, and you got no power? No, it ain't gonna be conservative. Which is why Green's theorem is then useful. This would involve a shit ton of work well, I haven't even told you what the curve is yet. I'll tell you this. C is the triangle with vertices at 0, 0, 1, 0, 1, 2. That's why it's unfortunate a few people left, because this is where you really see the power of this double integral. I know you guys still don't buy into double integrals. It's still relatively new to you, and they're like, oh my God, it's double. The work that would be involved for this directly becomes stupid simple with double integration. So right now, I don't know if you believe me or not. Can you guys just take a quick hot second and graph that triangle? And I would also say it's a positive orientation, which for some reason we've defined to be counterclockwise.
It starts going in the positive x direction and the positive y direction first.
And then the negative diagonal between the two. Yeah. Do you understand that if I wanted to do that interval directly, I have 3 separate paths. None of them are hard, but then I'm going to triple my work immediately, yes? Okay, I'd much rather do a double integral across that region, because all I care about then are the boundaries. I don't give a shit about anything. So here's what I mean. Can anyone tell me, all right, I'll do this one. This wall is x equals 1. Look at me go. This wall is y equals 0. Watch out, everybody. What's this wall?
Y equals 2x.
Do it again.
Y equals 2x.
Good, because this is just 0, 0, so that's kick-ass easy, yes? So if I want to do this, I need to figure out, so let me remind you. And again, if I were you, I would have this sitting next to me quite often. So down to the bottom, I've put Green's theorem. So now you know the form. What is P? XY. And what's Q? X squared y cubed. And what does Green's theorem need me to figure out in order to set up the double integral? Partials. Okay, good. So I need dq dx 2xy cubed, and I need dp dy. What's that? X. Kick ass. And then I can set up my double integral. I'm going to just put a d here for this d over there. Of dq dx minus dp dy. And I still have to figure out what order I want to do this in. Now, I think double integrals aren't as bad as you might have thought at first. Do you see how now, what's our choice we have to make? Now I'm completely back a few chapters. I am back a few chapters now. Now I'm like, which variable do I want to just go from this to this, and the other one I have to be careful from this wall to that wall? Yes? You draw your little barbell in there. So it's totally up to you guys. Since y is 2x, I might want to choose the inner one to be dy. I would agree. Yes? And let's see what else happens because of that choice. So what's dx? What's the limits on the outer interval? Holy shit. And then what's the limits on the inner one? So for any given x, you start here and you go there. I like it. So 0 to 2x. Okay, come on. So, oh my God. This, right off the bat, you would have to write 3 integrals for the 3 different paths. Yes? It's not conservative, so you can't say the answer is 0. So you have to do 3 different integrals for the 3 paths, and holy shit. This one says, screw that noise. Let me just do this. This is beautiful. I'm just taking a step back. I'm rewriting it in terms of a double integral of the derivative of the original single integral argument. Holy shit. So the inner integral kind of undoes that in a way you can think of. So I've introduced derivatives. So therefore, that's why I have a second integral. So that almost sounds like, why are you adding work to yourself? Well, no, because now I can look at it in a very different way. I can look at it as just cover that region. So if x goes from 0 to 1, y goes from there, I've covered the region. And how do you integrate this thing in the middle here? X, that's right, 2x, y to the 4th over 4, so we'll just do this. Is that cool? Minus xy, and I'm going to go from 0 to 2x. I almost don't care now, because, now, yes, that's easy, yes, maybe. So if I plug 2x in for y, I'll get 2 to the 4th is 16. Divided by 2 is going to be 8 in a minute. X times x to the 4th is x to the 5th. And when I shove a 2x into y here, I get 2x squared. And then that's an easy integral, so now I've totally lost interest. Is that okay? I need you to understand this, a lot of work. I convert it to this form, which is the dq dx minus dp dy form, much easier, which doesn't feel like it should be. It goes against intuition. Why would taking the derivative of stuff you got to work with and then making another integral, how could that make things easier? Because now it just changes my focus. Now I can look at it a different way. Okay, I don't know. Okay. Is that okay? I'm sorry. I took that away a little. Are you guys okay? I'm going to stop right there. You guys can keep going if you want to. I don't care. What is it going to be? 4/3 x to the 6 minus 2/3 x cubed, and you throw a 1 in there. Do you get 2/3?
Yeah.
Yes, okay, go away. Okay. Oh, yeah, that's a little side note. I'm not going to talk about that. All right, last thing for today. It's kind of a big idea, but we'll be okay. So one of the first major milestones in this class is when we introduce cross product and dot product. I don't know if you guys would agree. That's a while. Somebody's looking at me like, you are? That was huge, because we've used dot product and cross product in all kinds of ways. Do y'all agree? They're like the building block tools that we use in all these different situations. What we're about to do today is kind of like take those ideas up a notch. We're going to take the next level of tools on top of that. And one thing I forgot, which I'm going to pull it up anyway at some point. So, let's say I have a vector field defined on R cubed. I, j, k are just the coordinate unit vectors in the x, y, z directions. And we'll say the PQR partials all exist, yes? They don't exist, we have problems. So here's, all right. Then we define, did I want to do something first? No. The curl of F. So B, this is going to be gross, but then we're going to make it nice. All right, I almost don't want to write this, but I am. dr dy minus dq dz I hat plus dp dz minus dr dx. I'm going to make this much nicer in a minute. Plus dq dx minus dp dy. Does any of that look familiar at all? Isn't this exactly what we just saw in Green's theorem? So there's a way to rewrite Green's theorem using this idea of the curl of F. And there was a lot of, I've got a paper about a mathematical society meeting in the 1800s at some point, I think it was, where they discussed what to call this thing. And you guys don't get to, maybe I'll post it in Canvas, and I'm sure you guys are all like, oh good, I've been wanting some really obscure math history to read about, Jeff. That's fantastic. It's not cheesy curls, I don't want it. But they had to go through a whole idea, and they wanted to make sure they picked a word that didn't make it seem like what it wasn't. Curl does a decent job, we'll say. When I say the word curl, what do you think? Yeah, everybody's doing something like this, yes? So it inherently has some kind of rotation, and that was thrown around. They wanted to call it the rot of F, and they thought, no, it's not really rotation. It's a little different from that. So, okay. Does this whole thing look like something else, potentially? Does that whole kind of format of y piece minus z piece, z piece minus x piece minus y piece, cross product, kick ass. So here's what it is. You ready? Oh shit. Blah, 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 blah. So remind me what delta F is again? Yeah, so one way to write is fx, fy, fz. Let me write it in a more esoteric way. Just because. Is that cool? I could have put them out front, but it's okay. So look what this means. This by itself means this. It's just waiting to be multiplied by something so it can have something to work with, yes? That operator by itself is this. And if I multiply it by f, don't I just get this? Do you see how I just threw an f in each spot? Bam, bam, bam. It operates on f. So this isn't really multiplication, even though it looks like it. It's operation. If I operate on f with this, the f just goes into each piece. So this is like a square root symbol sitting there, and somebody else has got a 4, and I'm gonna put it in there, right? So this is the delta. That's like the square root symbol just sitting there. And the f is, I'm gonna bring an f, I'm gonna put it in, and when I do, bam, there it is. I don't know, are you guys with me? Square root symbol represents a process. The del operator represents a process. It requires an input to actually make sense, but that is what it does to an input. Okay, I think you've beat that to death, Jeff. Very true. So if I do this, it's a very different use of that freaking thing. How do I investigate this? Well, how do I do the cross product? What's the shortcut to doing the cross product? IJK. First vector. Well, what's this vector? What's this? It's this business, yes? So this will be d by dx, d by dy, d by dz. And then what goes down? What's f? PQR? Now, just to cut to the chase, when you do this shit, you get this. So whoever's noticed that that looked a lot like a cross product, it is exactly a cross product. What a curl does is it investigates how much a vector field wants to make something rotate. It's all about rotation. It's a little more subtle than that, and I'm running out of time, but if I compare it to its alternate, so you remember how there was a dot product and a cross product? And they kind of each were filling in what the other one missed, and they kind of together made a complete picture. I don't know if you guys remember this. The curl is this. It relates to the rotation of a vector field. So if I have a vector field that's just going straight out from the center, we've seen one like that. If I have a vector field xy, so at 1 it's 1, 1, at 2 it's 2, 2. At 2, 2 it's 2, 2. So it's just going straight out. The curl of that vector field would be 0. There is 0 rotation. It's purely radiating. Radiating? Sure, Jeff. Radiating. There's that missing syllable. So the curl takes care of the part, or kind of like if I apply it to a vector field, it tells me how much rotational aspect there is to the vector field at a point. This other dude, which just to cut to the chase, this is why this is so beautiful. If I use the curl to define one of these dudes, what do you think I'm going to use to define the other dude? No? I'm sorry, if I use the cross product, I was looking at this, that's the curl. If I use the cross product to define one of these new things, I'm going to use the dot product to define the other thing, and this is going to be called the divergence. Historically, they used to call it the convergence. So if I have a vector field that looks like this, and this would be like xy, this is pure divergence. It is going away from the center. So the divergence of that vector field would definitely not be 0. The curl of that vector field, completely 0. No point does it want to actually start to rotate. It's just going straight out. Yes? So if I had a vector field that was purely, we've seen one like this also, where it was just purely rotational and maybe they get bigger as they go out. That has got a divergence of 0 and a curl of definitely not 0. Bless you. Does that make sense? So it's kind of neat. I love this. The cross product looks at a vector one way, and the dot product looks at it another. The curl looks at a vector field one way, and the divergence looks at it in another way. Bless you. Bless you. Indeed. Nah. Oh, all right, so here, just to give you a couple of concrete examples, and next time I'll show you some pictures of these. That phrase always makes people, it's like a dinner bell or something. This would be purely radial. So this guy's curl would be 0, but the divergence would not be 0 for damn sure. This vector field, I think we graphed something like that together once, is purely rotational. No aspect of it. If I am born here, I will stay on this circle forever. You see what I mean? There's no way for me to go further away from the middle or closer to it. I am stuck rotating it. And if somebody else is born here, hey, they're stuck on that bigger circle. Maybe every now and again we're like, hey, hey. And if I'm born on this guy, I am flipping gone. There's no, I eternally get further away. There's nothing but go away. So for a random vector field, it's probably going to have neither one of these zero. So it's got a little bit of rotation and it's got a little bit of divergence. So an example of that would be something like this, except it's kind of going like this. Do you see how the rotation is happening, but it's getting further away at the same time? So it's got a little bit of curl, it's got a little bit of rotation, and it's got a little bit of divergence, a little bit of getting away. Yes?
You're making it seem like they're all kind of, well, I have to explain like if there was a function, it would just be like a primitive function, like that goes in the same direction with the same, okay, so the derivative doesn't change. Or, if you know what I'm saying, derivative is static. It doesn't have any more variables inside of it. So it doesn't go like any it doesn't
Oh, no,
change
no, no.
directions. It just
I want you to understand, the two examples I kind of focused on
Yeah.
were extreme examples. Yes? Just to show you a situation where the curl is zero and the divergence isn't, or the divergence is zero and the curl isn't, just to show the extremes. A random vector field, neither one of those will be zero. Yes?
What if it's like that? You know? Like
Yeah, totally. So neither one will be zero. It'll be some combination. And again, the curl and the divergence are all about at a point.
Okay.
So we've seen examples where they had like eddies,
Yeah.
where we had a vector field that kind of was doing stuff, and then here it had a little bit of a rotation. So the curl at a point in a vector field could be zero, but at another point it could be 3. I wanted to give two examples where everywhere one is zero and the other one isn't, and vice versa, right? But you're right, I love it. You're perfect. And how much time I've had to talk about this? Not much. But if I have a random vector field, then neither one's probably going to be zero. Yeah. And it should make sense, the curl being positive or negative relates to which direction the rotation is happening. Yes? Did I bring... Oh, that's perfect. Wait a minute. Is that true, Jeff? Did I make it as far as I wanted to? That's never happened before. Holy shit. And you're all like, yeah, you made it because you're going fast as shit. I'm sorry. So just the last thing I want to bring up. And next time I'll bring some concrete examples of curl and divergence, because we're just barely scratching the surface. Yeah. So here's the vector form of Green's theorem. Which is not his final form, so don't get too excited. So just to bring back these old favorites. So it's a closed curve. That's why Green's theorem would apply eventually. So this is what I was saying earlier. If I throw the curl in here, but I dot it with k. You guys noticed earlier that the k component is exactly what was inside a Green's theorem double integral. So if I just take the curl, but I dot it with k, that is another way to represent Green's theorem. The true last thing, what am I talking? I got more time. I normally just let you guys out early, but screw it. I can keep you here for the whole time one time. I want to show you something kick-ass. And I understand when I say that, you're like, I don't know, Jeff. Your definition of kick-ass is a little weird. Look at me go. I remember my password, everybody. I have to show you this. And I actually saved it in a nice form, and I forgot to bring it with me. So now I got to, let me first Google. Okay, good. And then I will look up Maxwell's equations. Okay. Here we go. Beautiful. Come here. No. Go back, Jeff. Just make it open the image. Bam. Haha, okay. Dude. This immediately ignoring the interpretations, anything looks familiar. By the way, there shouldn't be a period, it should be a dot, yes? Whatever I just picked, that should be in the middle. That should be del dot E, yes? So that's the divergence of the electric field is equal to rho divided by epsilon naught. Epsilon naught was the, oh my god, which one is it? Mu is the permeability, and epsilon is the permittivity. So there's two parameters of the universe that actually together manufacture the speed of light. So in a different universe, it might have had a different structure, it could have different values for those parameters, and the speed of light could be different. That's trippy. Why didn't you leave with that, Joe? All right. So the divergence of the electric field is this. The divergence of the magnetic field is 0. Magnetic field, if a charge enters a magnetic field, is going to go in a circle. Magnetic fields are all about rotations. Curl of the electric field is equal to the negative rate of change of the magnetic field. This one basically says a changing magnetic field causes an electric current. You guys ever heard of that? There's this experiment. Well, it's a pole, and you drop a magnet through it, and the pole is a certain metal, so it does this, and it will take forever to get down, because as it moves, it's a changing magnetic field. It sets up an electric field in the pole, which in turn sets up its own magnetic field, which opposes the magnetic field that created it. So it stops. When it stops, this is 0. This is 0. It goes again. Oh shit! It stops because it set up a thing, so it kind of goes down this pole. And if you put one that's not a magnet, it just goes. So it's a neat kind of thing to show. And this last one's the weirdest one off the top of my head. I can't even remember what the hell H is, to be honest. It's really bad, Jeff, but you'll be okay. I think this is a different form than what I'm used to. Yeah, I just pulled up a random thing. Who knows what this is? But these are the 4 main laws of electromagnetic spectrum. It's crazy. And you can immediately notice, you at least now know what the hell those symbols mean. Okay. All right, that's enough. I definitely wanted to at least get there, so I'm happy. Go somewhere and let your brain rest. Yes. Say again?
Can I see the vector form for Newton's theorem?
Oh, yes. Then I have to run. I have a meeting with the president at 2:30. I know.